Welcome friends, Igor is here, and in this video we will prove that being invertible is the same property as being non-singular. We have a fairly ambitious task in this video, and we will start by proving that a product of matrices is non-singular if and only if all terms in the product are non-singular. Then we will use this result to prove that a matrix is invertible if and only if it is non-singular, and we will show that if the coefficient matrix is invertible, then a linear system can be solved by using the inverse of this matrix. Let's get started. First is a technical result. Suppose we have two matrices A and B, which are square matrices of the same size. Then the product matrix A times B is non-singular if and only if both A and B are non-singular. This is an if and only if statement. This means there are two separate implications for us to establish. In the forward direction, we are going to assume that the product matrix is non-singular. Our goal is to prove that A is non-singular and B is non-singular. We are going to do this in two steps. In part 1, we are going to prove that the matrix B must be non-singular, and we are going to do it using proof by contradiction. We are going to assume the opposite of our desired conclusion, namely, on the contrary, we are going to assume that the matrix B is singular. By the definition of a singular matrix, it means that there exists a non-zero solution to the homogeneous linear system with B as the coefficient matrix. Let's call this non-zero solution vector Z. Then let's look at the following expression: matrix AB multiplied by the vector Z. Using the associative property of matrix multiplication, we can write this as matrix A multiplied by BZ. This simplifies to the matrix A times the zero vector. This is because we assumed that Z is the solution to the homogeneous linear system with B as the coefficient matrix, and therefore matrix B times vector Z is the vector of constants, which is the zero vector. But now any matrix multiplied by the zero vector is the zero vector. If you look at the beginning and the end of this computation, it tells you that Z is a solution to the homogeneous linear system with the coefficient matrix AB. But we know that Z is a non-zero vector, therefore it is a non-trivial solution to this homogeneous linear system. In turn, this means the coefficient matrix of this system, which is the matrix AB, is a singular matrix. But this is a contradiction. Do you see what the contradiction is? We assumed that the matrix AB is non-singular, and yet we derived that it also must be singular. A matrix cannot be both non-singular and singular at the same time, so something went wrong. What was the cause of this contradiction? Well, this contradiction was obtained because we assumed that the matrix B is singular. Therefore, this assumption is impossible. The matrix B must be non-singular. We completed the proof of the first part, and we proved that if AB is non-singular, then the matrix B must be non-singular. Now, we proceed with part 2, where we will prove that the matrix A must also be non-singular. Similarly to part 1, we will use proof by contradiction. On the contrary, we will assume the opposite of the desired conclusion. We will assume that the matrix A is singular. This means the homogeneous linear system with A as the coefficient matrix has a non-trivial solution. So let's choose one such non-trivial solution and let's call it vector Y. It is a non-trivial solution, therefore it is a non-zero vector. And now the trick is to look at the linear system with B as the coefficient matrix and this vector Y that we just found as a vector of constants. Let's use what we already proved in part 1. We already know that the matrix B is non-singular, and therefore any linear system with B as the coefficient matrix has a unique solution, no matter what the vector of constants is. Therefore, we can conclude that this linear system has a unique solution, and let's call this unique solution vector W. In particular, it means that matrix B multiplied by the vector W is equal to the vector of constants, which is the vector Y. One important observation before we proceed: this unique solution W that we just found is a non-zero vector. This is because matrix B times the vector W is equal to the vector Y, and we assumed that the vector Y is a non-zero vector. So if W were the zero vector, then BW would also be the zero vector, which is not the case. It follows that the vector W cannot be the zero vector. And now let's look at the following expression: matrix AB multiplied by the vector W. We can use the associative property of matrix multiplication to rewrite it as matrix A multiplied by the vector BW. And we know that B times W is the vector Y. Finally, the matrix A multiplied by the vector Y is the zero vector, because the vector Y is a solution vector to the homogeneous linear system with A as the coefficient matrix. Now, if you look at the beginning and the end of this computation, you will see that it tells you that the vector W is a solution to the homogeneous linear system with AB as the coefficient matrix. Moreover, the vector W is a non-trivial solution. Why? Because we already know that it must be a non-zero vector. But this is a contradiction, because on the one hand we assumed that the matrix AB is non-singular, on the other hand we showed that it is also singular. These two statements cannot coexist. What was the cause of this contradiction? This was caused when we assumed that A is a singular matrix. Therefore, A cannot be a singular matrix. If it cannot be a singular matrix, it must be non-singular. And this is exactly what we were trying to prove. This concludes the proof of the forward direction, because we proved if the product matrix is non-singular, then B must be non-singular and A must be non-singular. In the opposite direction, we are going to assume that we have non-singular ingredients. Let's look at the homogeneous linear system with AB as the coefficient matrix. And let's take any solution of this linear system, a vector x. We know that every homogeneous linear system is consistent, therefore there is at least one solution. Then, using our matrix vector product notation, it means matrix AB multiplied by the vector x is equal to the zero vector, which is the vector of constants in the homogeneous system. Let's use the associative property of matrix multiplication to rewrite the left-hand side as matrix A multiplied by the product of the matrix B and vector x. But this means that when you take a matrix A and multiply it by B times vector x, you'll get the zero vector. In turn, it means that matrix B times vector x is a solution vector to the homogeneous linear system with A as the coefficient matrix. But we assumed that A is a non-singular matrix, and therefore this homogeneous system has only the trivial solution. Therefore, the vector B times x, which is a solution to this linear system, must be the zero vector. But now, this in turn means that the vector x is a solution to the homogeneous linear system with B as the coefficient matrix. And we assumed that the matrix B is non-singular. It means the vector x must be the zero vector, because this linear system has only the trivial solution. So, let's recap. We started with the homogeneous linear system, which has the matrix AB as the coefficient matrix. We took an arbitrary solution vector x of this linear system, and we proved that this vector x must be the zero vector. This means that this homogeneous system has only the trivial solution. And this is precisely the definition of a non-singular matrix. The coefficient matrix of this linear system is non-singular. This completes the proof of the opposite implication, and therefore this completes the proof of the if and only if statement. The advantage of if and only if statements is that they work in both directions, and therefore if we proved that the product of two matrices is non-singular if and only if both individual matrices are non-singular, in turn this means that the negations of these two statements are also equivalent. In other words, the product matrix is singular if and only if at least one of the matrices A or B is singular. Please note how the negation of the statement both A and B are non-singular is at least one of A and B is singular. The negation is not both A and B are singular. And now I urge you to pause and think. Does this arise any associations with properties of products of numbers? Let me give you a hint. Suppose you have a product of several numbers that is equal to 0 or not equal to 0. What can you say about the individual numbers in this product? Please write what you think about this down in the comments below. What are the associations that you see between the properties of matrix products and properties of the number products? In the previous video, we constructed a procedure that allows to compute the inverse of a non-singular matrix using the Gauss-Jordan elimination. Yet, that procedure in fact constructed only one-sided inverse. If you start with the non-singular matrix A, you were guaranteed a matrix B, so that A times B is the identity matrix. But that procedure did not tell us anything about the other product, B times A. Now we are going to prove that if you have two square matrices A and B such that A times B is the identity matrix, then the other product, B times A, is automatically equal to the identity matrix, and therefore this procedure from the previous video indeed is sufficient to compute the inverse of a non-singular matrix. I think we've had enough proofs by contradiction for today, so let's do a direct proof. So we're going to assume that A times B is equal to the identity matrix. We know that the identity matrix is non-singular. For example, because its reduced row echelon form is the identity matrix. So this means the product A times B is non-singular. By what we just proved, both A and B must be non-singular. And here's an ingenious trick. Because B is non-singular, we are going to apply that Gauss-Jordan elimination procedure to construct a square matrix C so that B times C is equal to the identity matrix. Now we're all set to prove that B times A is the identity matrix. Let's use a simple but effective trick. I'm going to multiply this matrix by the identity matrix, and of course it is equal to the original matrix. But I'm going to replace the identity matrix with the matrix B times C. Next, I'm going to apply the associative property of matrix multiplication. Now, it's about time to use our assumption that A times B is the identity matrix. This product simplifies to B times C, which we already know is equal to the identity matrix. Bingo! So we've covered a lot of ground with respect to invertible matrices, so let's pause and try to summarize what we discovered. If we start with a non-singular matrix A, then we have a procedure that constructs a matrix B such that A times B is equal to the identity matrix, and this can be done by performing the Gauss-Jordan elimination on the big matrix, which is constructed by taking the matrix A and putting to the right of this matrix the identity matrix. We reduce this matrix, and from the reduced row echelon form we take the right half. This right half is exactly the matrix B we're looking for. The previous theorem that we just proved tells us that this matrix B will automatically satisfy the equation B times A equals the identity matrix, and therefore this procedure allows us to construct an inverse for any non-singular matrix A. In turn, this implies that every non-singular matrix is automatically invertible. But this still leaves the question of what happens with singular matrices. Now, it should be clear that this procedure fails for singular matrices because when you try to construct this big matrix for a singular matrix, the singular matrix itself will not reduce to the identity matrix, and therefore this procedure cannot be applied. But just because this procedure fails, it doesn't mean there is no other procedure that will possibly find an inverse for a singular matrix. So, we are going to prove that in fact there is no other procedure. Singular matrices are never invertible. And this is encoded in the following result. A square matrix is invertible if and only if it is non-singular. We defined the non-singular property of a matrix using solutions to homogeneous linear systems. And we defined the invertible property of a matrix as a property of matrix multiplication. It turns out that these two properties are in fact the same property. This is simply two different angles of looking at the same phenomenon. Are you excited about this result now? Then let me show you the proof. This is an if and only if statement, therefore there are two implications for us to prove. In the forward direction, we are going to assume that we have a non-singular matrix A. Our goal is to prove that it is invertible. But we already know this, right? If you start with a non-singular matrix, we have a procedure that constructs a matrix B such that A times B is identity. And we also proved that this matrix B automatically satisfies the equality B times A is equal to identity matrix. This means this matrix B is the inverse of A, and hence A is invertible. It is the implication in the other direction that's going to be new for us. We are going to start with an invertible matrix A, and our goal is to prove that this matrix must be non-singular. Well, because A is invertible, it means there is an inverse matrix, and in particular A times inverse of A is equal to the identity matrix. But the identity matrix is a non-singular matrix, therefore the product of a matrix A and inverse of A is a non-singular matrix. And today we proved that if the product is a non-singular matrix, then both matrices must be non-singular. In particular, it means that the matrix A is non-singular. And this completes the proof of this beautiful if and only if result. Good news, it means we can extend our list of equivalences for a square matrix, namely, a square matrix is non-singular if and only if it is invertible. Because this is an equivalence, it can also be phrased in the following way. A matrix is singular if and only if it is not invertible. So, non-singular matrices are the same as invertible matrices. Singular matrices are the same as non-invertible matrices. Finally, let's connect our new discoveries with solving linear systems. If we have a linear system with a non-singular coefficient matrix, then we know that this linear system has a unique solution no matter what the vector of constants B is. But now we know that if you have a non-singular matrix A, it does have an inverse matrix. So what we are going to prove now is that the unique solution of the linear system with a non-singular matrix A as the coefficient matrix and B as a vector of constants is in fact equal to the inverse of A times the vector of constants B. In other words, if you know the inverse of the coefficient matrix, then to find the unique solution to the linear system, all you have to do is to multiply the inverse matrix by the vector of constants. Let's prove this. The assumption that the coefficient matrix A is non-singular tells us that this linear system has a unique solution. So, let's show that A inverse B is one of the solutions of this linear system. To do it, we take the coefficient matrix A and we multiply by this vector, which we suspect is the solution vector. We use the associative property of matrix multiplication to rewrite this as follows, and the matrix in parentheses becomes the identity matrix. Identity matrix times vector B is just vector B. So this shows that the vector A inverse B is a solution of this linear system, but we also know that this linear system has a unique solution. Therefore, this vector is the solution of the linear system. If you found this video useful, even though it was a little long, then please give it a like to help others discover this content, and of course subscribe to this channel to see more of these videos. In the next video in this series, we will talk about the column space of a matrix. And by now you know that you can always count on me, so I will see you later.